So today we're going to cover section 2, and we're going to talk about independent and dependent events. So first we need to define what it means to be an independent event versus a dependent event. So two events are independent events if the occurrence of one event does not affect the occurrence of the other. So for example, if I'm spinning a spinner and I spin it and I want to know what's the probability of my spinner, say if it's separated into 4 colors, landing on red. When I spin it again, that spinner, the probability of the second spin has nothing to do with what happened on the first spin. So that's when the events are independent. Or let's say you're flipping a coin and rolling a dice. Okay, what happens when you flip the coin has nothing to do with flipping the coin or rolling the dice. They're two independent events. Now, when two events are dependent, that's when the occurrence of one event affects the other. So like the picture there. Let's say you have a jar of marbles. If it asks you what's the probability of drawing a red marble first and then a blue marble second, when you don't replace the marble after you pick the first one, that would be considered a dependent event, because once you take out a marble from the jar, then the probability that you're going to calculate for pulling the second marble will change. So when after you do the first event, if its results affect the second event, then the events are considered dependent. So let's look at our first example. Tell whether the events are independent or dependent. A box contains yellow and brown dog treats. You randomly choose one dog treat from the box and you do not replace it. Then you randomly choose another dog treat. So after you choose the first dog treat and you get yellow, and then you want to choose a second one to get brown, will the two events be affected if you don't replace the first dog bone? It will change the probability. So let's give this some numbers so it looks a little bit better. So let's say we have 4 yellow dog bones or treats, and then we have 6 brown. What would be the probability of choosing a yellow dog treat? How many dog treats do we have in total in the box? We have 10, right? 4 plus 6. How many of them are yellow? So we would do 4 over 10. That would be the probability of event A, correct? And then we could simplify that to 2/5. Now, what if we start from scratch and all 10 dog bones are in there? What's the probability of brown? 6 over 10, which would be 3/5. So this is if we were to take the dog bones and put them back, the probability won't change. But let's do it now, and let's say, all right, we pick the dog bone and we keep it. We give it to our dog. Now what would be the probability? So now we've picked the dog bone, the first one, and we got the yellow one. So now I'm going to change this to a 3. How many dog bones are left for us to calculate now the probability of event B, now that I took one out of the box? How many are left? 9. And how many of them are brown? 6. And then I can reduce it, and now it's 3. I can divide this by 3 and get 2 to 3, or 2/3. Does that make sense? So when you don't replace something, the probability is going to change. If you replace it, then the probability will stay the same. And there's going to be a formula we're going to see here. So when you take something out of a jar or out of a box, or you select something and you keep it and don't return it, and then you have to calculate a second probability, that's considered a dependent event. But when you replace it, then it's independent. So let's try another one. The marbles. So a jar contains red and blue marbles. You randomly choose a marble from the jar and then replace it. And then you choose another marble. What's the probability? It's asking you for the probability of A and B. So is this going to be independent or dependent when you replace it? When you replace it, it's independent. If I don't replace it, it's dependent, because it depends on what you chose the first time. But in this case, when we replace it, we're going to look and say, oh, I got a red one the first try. Let me put it back in the jar, and now let me pull my second marble. So this would be considered an independent event. The formula for conditional probability, and this is when you don't replace it. The probability that event B occurs, given that event A has occurred, is called a conditional probability. And it's the probability of B given A, and it's written probability of B, and then equals probability of B slash A. So what you're going to do is you're going to take into consideration that event A happened, and you've decreased the total that you have. And we're going to see this with numbers, and it'll make more sense. These are the two probabilities for formulas for independent and dependent. So when the two events are independent, they have nothing to do with each other, you're just going to do the two simple probabilities and get those results and multiply them. For dependent events, we're going to use that conditional probability. We would do the simple probability of event A happening, and then for the probability of event B, given that A took place, will be written here. And we're going to see this with numbers. Now, this is just how the conditional probability formula comes about. They're just taking it and dividing it by the probability of A, which gives us the formula that we need. So let's try our first example. We have a spinner, and it's divided into 8 equal parts. It wants us to find the probability that you get red on your first spin and blue on your second. Now, will this be considered an independent or a dependent event? Will the second spinner's results have anything to do with the first? Is it going to change anything? No, right? Because we're not taking a color off of the spinner once it lands on that. So when you're dealing with the spinner, this is going to be considered an independent event. So what we're going to do is classify what happens on each spin. So event A is going to be, we're going to get red on the first spin. Event B is getting blue on the second spin. So because these are two independent events, to calculate the probability of both A and B occurring, I'm going to take the simple probability of A, and I'm going to multiply that to the probability of event B. So what would be the probability of my spinner stopping on a red space? Okay, how many red colors do we see? 3. So there's 3 red over 8. How many blue spaces do we see? 2 over 8, right? So because when I spun the spinner the first time and I got red, I'm not taking away that space and decreasing the number of red spaces. The spinner's going to stay intact. So it doesn't change the probability for blue. Now I multiply these two results. I'm going to write it as a simplified fraction. a decimal, and a percent. I'm going to simplify before I multiply here. I'm going to change the 2/8. I'm going to change this to 1/4. The 3/8 I can't simplify. And then I'm going to multiply what's left. So the probability written as a fraction is 3/32. As a decimal, 0.094. As a percent, move it 2 times, 9.4%. So be able to recognize answers for these word problems as fractions, decimals, or percents, just in case you end up with a multiple choice question. So this was an example of an independent. Now what we're going to do is do a dependent situation. We have a bowl of grapes. We have 36 green, 14 purple. We're going to randomly choose a grape and we're going to eat it. And then randomly choose another grape. It wants us to find the probability that both events A and B will occur. So what they're asking us to find is the probability of A and B. And again, this is going to be written as, because it's dependent, because I've eaten the grape, I didn't put it back in the bowl, I'm going to be doing probability of A times the probability of B, given that A has already happened. So this is an example of dependent. So what is the probability of event A happening? How many green grapes do I have? I've got 36. How many total grapes are in the bowl? I'm going to add 36 plus 14, and I have a total of 50 grapes. I can reduce this. I can divide them both by 2, and it simplifies to 18/25. Now, here is where the dependent comes into play. When you're doing a problem like this, you're going to assume that event A happened, that you got that green grape, you took it out of the bowl, and you ate it. How many green grapes are left now? If you took one away and ate it, there's now 35 green grapes out of a total of 49 grapes left in the bowl. So the probability of event B, given that A happened, is 35/49. I have to multiply that with the probability of A, which was this 18/25. Now, we need to write this as a simplified fraction. I can also simplify 35/49, and that will reduce, I can divide them both by 7, and this will simplify to 5/7. I'm going to rewrite this one right next to it. Now before I multiply, I can still simplify further. I can simplify the 5 and the 25, change that to a 1, change that to a 5, and then my final answer here is 18/35. So that would be the probability of both A and B occurring. As a decimal, it's going to be 0.514, and as a percent, 51.4%. So again, be able to recognize your answer as either a fraction, decimal, or percent. So whenever it's dependent and you're taking something away, you're going to assume that event A happened. You got that green grape and you ate it, and now you've reduced the number of green and the number of grapes in the bowl. Let's try example 5. Tell whether it's independent or dependent. So a drawer contains 12 white socks and 8 black socks. You randomly choose one sock and you do not replace it. You randomly choose another sock. What is the probability that both socks chosen are white? So when you do not replace it, this is considered a dependent event. So this is dependent. So again, let's identify our events. So event A is going to be that you get the white sock on your first pick of the socks. Event B is you're going to get a white sock the second time. So because it's dependent, the formula I'm using, so the probability of both event A and event B happening, because it's dependent, I do the probability of A times the probability of B given that A happened. So I'm going to count the total number of socks I have. 12 plus 8, so I have 20 socks. So my probability of event A is 12 white over the total. I can simplify this. I can divide them both by 4, and it becomes 3/5. Now, the probability of event B, given that A happened, remember you're going to assume that when event A took place, you got that white sock. So now there's only 11 white socks left and a total of 19 socks left in the drawer. You'll take that probability and multiply it with the probability of A. Nothing will simplify here. So this will simplify into 33 over 5 times 19 over 95. When I divide that as a decimal, 0.347, and as a percent, 34.7%. So again, recognize it as a decimal, fraction, and percent. Now let's do number 2. This time we're going to flip a coin, and we're going to flip it twice. What is the probability you get tails on the first flip and tails on the second flip? So after I flip my coin, is the probability of the second flip going to change after I flip it the first time? No, right? It's not like I'm taking the tail away. It still stays the same coin, and the probability will stay the same. So event A is going to be the probability that I get tails on my first flip. And event B means I get tails on the second flip. So because they're independent, the probability of A and B is going to be probability of A times the probability of B. So the probability of flipping a coin and getting a tail, there's one tail out of 2 outcomes, and the same thing for the second flip. So 1/2 times 1/2, and the probability as a fraction is 1/4. As a decimal, 0.25, and as a percent, 25%. So again, be able to recognize all 3 forms. So this is considered an independent event because what I get on my first flip does nothing to my second flip. Now we're going to try an example given some data from a table. So here, this table shows the number of tropical cyclones that formed during hurricane seasons from 1988 to 2004. It says use the table to estimate, for the part A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So what we need to do is figure out how many tropical cyclones happened in the northern hemisphere, and then figure out how many of those were hurricanes. So I need to total up this column. So I'm going to add 199 plus 398 plus 545, and that gives me 1142. This is going to give me everything that happened in the northern hemisphere: the tropical depressions, tropical storms, and hurricanes. So out of all those tropical cyclones, I want to know the probability that it was a hurricane. So probability that it was a hurricane in the northern hemisphere out of all the cyclones. So I'm going to put the number of hurricanes in the northern hemisphere over the total number of tropical cyclones in the northern hemisphere. So total number of hurricanes was 545, and all the storms together, the depressions, the tropical storm, and the hurricane, added to 1142. As a decimal, 0.477, and as a percent, 47.7%. For part B, it wants to know what's the probability that a hurricane is in the northern hemisphere. So what I need to do is figure out the total number of hurricanes. So from the chart, I'm going to add this way and get the total for the number of hurricanes between the two hemispheres. And that's going to be 760. And then I take what I'm trying for, which is the hurricanes in northern, which is the same numerator I had before. So for part B, it'll be probability that it's a northern hemisphere and it's a hurricane out of the total hurricanes. So number of hurricanes in the northern hemisphere over total number of hurricanes. So this is going to be 760 and then 545 on the top. As a decimal, 0.717, and as a percent, 71.7%. More than likely on the word problems, they would look for it as a percent. And then one last example, we're going to talk about a deck of cards. The last example says you randomly select 2 cards from a deck of 52 cards. What is the probability that the first card is not a heart and the second is a heart? We're going to do it first with replacement, and then the second time we're going to do it without replacing it. So let's identify the events. So event A is the first card is not a heart. Event B, second card is a heart. All right, so when we replace the card for the answer to part A, so when we replace, that makes it independent. So here what I'm going to be doing is the probability of A and B, and we just do the two simple probabilities and multiply them. So the probability that a card is not a heart, so there are 13 cards in each suit. So there's 13 clubs, 13 spades, 13 diamonds, 13 hearts. So not a heart would be 52 minus 13, which would be 39 over the 52. And then event B, second card is a heart, because we replaced it, is 13 over 52. Now I can simplify these fractions. I can divide 39 by 13 and 52. So this fraction will simplify to 3/4. And then this one will simplify to 1/4. I can multiply, and I get 3 over 16. As a decimal, this becomes 0.188, and as a percent, 18.8%. Now this is with replacement, so it's independent. Without replacement, when I choose the first card and I keep it, that's going to change the probability. So for part B, this is without replacement, so I don't replace it. This makes it dependent. So that's going to be written as probability of A and B. And that's going to be the probability of A times the probability of B given that A happened. And again, you're going to assume you got that card that was not a heart. So the probability of not a heart stays the same. This one is 39 over 52. Again, I can reduce that to 3/4. But the second probability of B, given A happened, so I pulled the card out. So now I only have 51 cards to choose from, and I got my heart. So then now what's going to happen is, now there's only going to be, or I didn't get the heart, sorry. So this stays the same, the 13, because all 13 hearts are still in there because event A was not a heart. Now, I can also simplify. Let me go ahead and put this down here. I can also simplify diagonally the 3 and the 51. 3 goes into 51 17 times. I'm going to multiply what remains, and I get 13 over 68. And then turn that into a decimal, 0.191. As a percent, 19.1. Those would be your 3 answers. And that is it for dependent and independent events.